Hello everyone, myself Srivalli, working as an assistant professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today, the overview of presentation includes types of relations. So first one, in the types of relation, the very first one is universal relation. So what is meant by universal relation? So a relation capital R from set A to set B is said to be universal if R is equal to A cross B. So here, let capital R, we can say that this is a relation. And let us suppose we have two sets which are denoted with set A and set B. Now they are said to be universal. So we can say that this R from the set A set to set B is called universal if R is equal to A cross B. So example, here for example, A is equal to 1, 2, B is equal to A, B. So let us suppose set A is equal to 1, 2, B is equal to A, B. Now R is equal to 1A, 1B, 2A, 2B. And we can say this is called a universal relation. So how we can say that this is called a universal relation is, we are just multiplying A with B. So that is 1A, 1B, 2A, 2B. So like this we are just multiplying here. This multiplication of these two sets is called universal relation, which is nothing but whole. Universal is nothing but all the elements will be included, all the ordered pairs will be included here. So a relation capital R on a set A is said to be universal if R is equal to A cross A. For example, they have given only set A. And how to find out the universal relation is, so you have to consider another set A, the same set A you have to consider, and you need to just multiply with that A and you will get the elements. For example, see, that is the example also we have given here. A is equal to A, B, then R is equal to AA, AB, BA, BB. So how we are multiplying AA, that means 2th element, means which is nothing but A cross A we are doing, which is nothing but A, B, and here also A, B. So now we are just multiplying here A, B, B, A and B, B. So AA, AB, BA, BB. So like this, here we have multiplied, and this relation, whatever the given relation you got, this is called universal relation on which the capital A, whichever they have given. This is called universal relation. Next we have complementary relation. So complement of a relation will contain all the pairs where the pair do not belong to a relation but belongs to Cartesian product. So that is nothing but, see for example, set A is equal to 1, 2, B is equal to 3, 4. So R is equal to 1, 3, 2, 4. And A cross B is equal to 1, 3, 1, 4, 2, 3, 2, 4. And the complement of relation is, see this RC is nothing but will denote like this only. RC is equal to 1, 4, 2, 3. What is the meaning of this? See here, 1, 2. A is equal to 1, 2 we have, B is equal to 3, 4. So find the complement of R, or sometimes they'll be asking the question, find R power C. R power C is nothing but you need to understand that this R power C is complement of the relation. So now if you want to find out the complementary relation, they have to give the relation also. So in the question they'll be giving mention the relation also. What is that relation they have given? 1, 3 and 2, 4. For this you need to find out the complement. So if you want to find out the complement, so first you need to understand, first you need to find out A cross B. Means A cross B is nothing but what? Universal relation. From the universal relation, if you subtract this given relation, then you will get the complement relation. So A cross B is what here? 1, 3, 1, 4, 2, 3, 2, 4. This is universal relation here. Now, if you do subtract the given relation, means here 1, 3 and 2, 4, I am going to cancel it. And what is the leftover relation here? 1, 4 and 2, 3. This is the given one. So this is like how to find out the complement of the relation. Next we have inverse of a relation. Inverse is nothing but just interchanging the values in the ordered pair. So see here, An inverse of a relation is denoted by R power minus 1. R inverse we can call, which is the same set of pairs, just written different or reverse order. Reverse order, we'll just interchange it. Let capital R be any relation from A to B. The inverse of R is denoted by, let us suppose we have some relation R. So like this 2, 3, 3, 2, 4, 1, like this we have. The inverse of R is denoted by here R power minus 1 is equal to, so you'll just interchange the values, that is 3, 2, 2, 3, 1, 4. This is like how to find out the inverse relation. So here the same, like this only we have example here. R inverse is equal to, this is like official formula here, formal one. So y comma x colon y belongs to B, x belongs to A, x comma y belongs to R, which is nothing but whichever the ordered pair you are getting, just like this one, y comma x you will get in place of x comma y. And that y should belongs to capital B, x belongs to A. For every x comma y belong, means if x comma y is itself is belonging to R, then only you will get y comma x, where y is belonging to set B, x is belonging to set A. Now let us see here the one more example we have here. R is equal to 1, 4, 2, 3, 3, 4. Now R inverse is equal to 4, 1, 3, 2, 4, 3. Means we are just interchanging the values in the ordered pair. So next we have composite relation. So what is meant by composite relation here? Let us consider a relation R and another relation S. So the composite relation of two relations. So previously we have considered only relations like only one relation, that is R. But here we have considered two relations, capital R and capital S. So the composite relations of these two relations be a relation which is denoted by R circle S, R composite S. So we can call it as circle or composite. And this is defined as, how you will get R circle? How to find out R circle S? So A comma C means you will get A comma C such that A comma B belongs to R, B comma C belongs to S. Means you will get the answer for R circle S as in the form of A comma C. But if at all, if A comma B is belonging to R and B comma C is belonging to C, this is like transitive, but they are belonging to different relations. So A comma is belonging to one relation R, B comma C is belonging to another relation S. Based on this, you are getting the answer for R circle S in the form of A comma C. Previously for transitive, everything will be checking in only one relation. If AB is there, BC is there, AC also should exist in the relation. If that as it is following, then we can say that the given relation is called transitive relation. But here, to get the circle R circle S here, R circle S is in the form of A comma C, but whenever A comma B belongs to R and B comma C belongs to S here. Now hence A comma B belongs to R, B comma C belongs to S, A comma C should also belong into R circle S, R composite S here. Let A is equal to 1, 2, 3, 4. R is equal to 1, 2, 2, 3, 2, 4. So S is equal to 2, 1, 3, 4, 4, 2. And we are getting R circle S as 1, 1, 2, 4, 2, 2. How we are getting? So set A is equal to 1, 2, 3, 4. Now R is equal to, first one is 1, 2. Let us represent it as A comma B. And that B comma C should exist in the relation. Means the order pair which is starting with B. B is nothing but what here? 2. The ordered pair which is starting with 2 in the S, I need to check. So 1, 2 is there and 2, 1 is there. So 1, 2, 2, 1 is what? AC 1, 1. So like that you just check it out whether we have the other ordered pair also in the S starting with 2, but we don't have. Let us leave it. Next, go for the next one and represent it as 2, 3. Just denote it as 2, 3. Now, if 2, 3 is there, you need to check for whether 3, 4 or whether starting with ordered pair 3 is there or not. So 2, 3 is there, starting with ordered pair 3 is there, then you can go for 2, 4. Here we have 2, 4. Now 2, 4 is there, starting with ordered pair 4, it is there. 2, 4, 4, 2, that is 2, 2. Now if we observe, this is called R circle S, R composite S here. Next we have composite relation. So a relation capital R on set X is said to be compatibility relation. So this is compatibility relation if and only if it satisfies two properties. So here a relation capital R on set X is said to be compatibility relation if and only if it satisfies two properties. Those are reflexive and symmetric. If the relation is also satisfying transitive, then we can say that is called equivalence relation. But up to here, if only two relations are satisfying, then we can say that is called compatibility relation. Let us consider one example here. Let A is equal to 1, 2, 3 and R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 2, 1, 3, 2, 1, 3, 3, 1. Now, here I need to check whether this is a compatibility relation or not. So, compatibility relation means a relation which satisfies reflexive and symmetric. So, what is meant by reflexive here? I should have the elements, how many elements are existing in set A? 1, 2, 3. So, all the elements should exist in the form of A, A. So, 1, 1 is there, 2, 2 is there, 3, 3 is there. So, it is satisfying the reflexive property. Next, let us go for symmetric here. What is meant by symmetric property? If 1, 2 is existing in the relation, if 2, 1 is also existing in the relation, then we can say that it is called symmetric. That is nothing but A, B is existing means B, A also should exist in the relation. Then we can say that it is called the here symmetric property. So here 1, 2 is there. 2, 1 is also existing here and 3, 2 is there and 2, 3 is also existing here. 1, 3 is there and 3, 1 is also existing in the relation. So, if you observe here, as all the relations are in the form of A, B and B, A, then we can say that this is called a symmetric relation. So, as these two relations are satisfying here, we can say that the given relation R is called compatibility relation. So that's all about today's session. So today what we have discussed is, so we have discussed about what are the types of the relations like universal relation and composite relation, complementary relation, compatibility relation. So like that we have discussed about the types of the relations and how to represent the relations. So that's all about today's session. So thank you.